All right. Um, so this week we're going over friction and drag forces. Before I start, I want you guys to go into the description of this video and click on the sign in link and please sign in. That helps me out. It helps me to sort of track attendance, and it's kind of hard for us to get attendance right now because the whole Zoom thing. So if you guys could do that, that'd be awesome. Really help me out. Okay, let's get started. So friction, we're gonna start with friction. Okay, so a 10 kilogram block is initially at rest when a 30 Newton force is applied to it horizontally. The static friction coefficient is 0.25 and the kinetic friction coefficient is 0.05. Will the block move? Okay, so will the block move? That's the question. So we have to sort of define the difference between static friction and then kinetic friction, right? So static friction, if you think about it, what is a static object is something that is not moving, right? Kinetic, you know, any like kinesiology, it's the study of movement in the muscles, right? So it's kinetic is when something is moving, right? So static friction is what we're going to be looking at right here, right? Because we want to know essentially how much force do we need to push on the block in order to get it to start moving, right? And once we know that, we will compare it to the force that's being applied to this block. And if that force is stronger, then we know that our block's going to be moving. If it's not stronger, then our block is not going to be moving. Okay, so let's do this. So how do we do this? Well, there's like simple formula. So F equals mu S times N, okay? So if we draw out this, so we got essentially N, what N is just mass times gravity, right? So if we substitute mass times gravity here, so F equals mu static times this, which is mass times gravity. Okay, so this is essentially how much force is going to be applied, right, downwards. Okay, so that's important, right? Because we know probably, the bigger the object, it's going to be harder to move at the start, and that makes sense in this equation because as we increase mass, whatever fraction of that force is going to be increasingly larger as we increase mass, right? You can think of the static coefficient as sort of like a fraction, and the as like so like in this case it's like 0.25, right? So when we plug in all of our numbers, right, our force is going to be 0.25. So it's like 25% of, we're going to need at least 25% of our force due to gravity to overcome, right, the static force. So 9 times 9.8. Okay, and when you do the math, what do we get? So we get that this force that we need to overcome is 24.5 newtons. Okay, so we need a force of 24.5 newtons at least to overcome the stats, right, to get it to start moving. So then when we look at our problem, we have a horizontal force that is 30 newtons. Okay, so it's perfect. It's above our sort of like basal level of force that we need. So will our block move? Yes, my block is going to move. My answer sheet, I said no. I don't know why, but anyway. Cool. Okay, number 2, a 3 kilogram block is at rest. Okay, good. It's at rest on a table. The static friction coefficient is 0.40 and the kinetic friction coefficient is 0.10. Then a 20 Newton horizontal force is applied to the box. What is the magnitude of the box's acceleration? Okay, cool. We want to know the magnitude of the box's acceleration when we're applying this horizontal force. Okay, so the first thing that you should always do, check if the box is moving, right? So that's always good practice here. So is our box moving? So what do we have to use to find out if our box is moving? Well, we have to use the static friction coefficient, right? We have to find out if our force, which is 20 newtons, is going to overcome sort of the basal force that we need to apply to this block. Okay, so let's see about that. So when we do it, right, F equals mu, which is in this case 0.40 times mass times gravity. 3 times 9.8. That equals 11.76. Okay, newtons. Cool. So we need at least 11.76 newtons to overcome the static force of friction, and we have 20, right? So we're chilling. Okay, so this is static. Let's see, label it. Okay, so let's draw out sort of a little diagram. Okay, so our box is being pushed, let's say, to the right with 20 newtons of force. Okay, so let's say we just disregarded friction for a second, right? Let's say there was no friction in it. I could pretty easily find out the acceleration of this box, right? 20 newtons of force being applied to it. I just divide that by the mass and I can get acceleration, right? But, all right, we can't do that in this case because we have some sort of friction being applied, right? Some sort of force in the opposite direction is being applied. Okay, so essentially what we have to do is we have to find out what the magnitude of that force is in the opposite direction and then subtract it from the force, the 20 newtons, right? And that'll be our net force acting on the object. And then we can do divided by mass and get our acceleration. Okay. So when we do that, we have to, since the box, we know our box is moving, we have to use kinetic friction. So our coefficient is 0.10, right? So let's look at the friction. Kinetic friction, 0.10 times 3 times 9.8, right? And then that gives us 2.94 newtons. Okay, so we know that our force in the opposite direction, right, our friction force, is that. Okay, so now when we do our F net equation, that equals 20. Let's say 20 is in the positive direction, plus a negative. So that's a negative direction, 24, right? Because it's negative, it's in the opposite direction. So then our F net equals, in this case, 17.06 newtons. Okay, and then we know, again, right, simple equation, F equals ma. We know the mass in this equation, so if our F is 17.06, our mass is 3 kilograms, then we know our acceleration is 5.68. We'll just round that to 9 meters per second squared. Okay. Yeah, so that's our acceleration of our block. So we have to take into fact the friction force when we do this. All right, number 3. So a 30 kilogram box is at rest on a ramp with a static friction coefficient of 0.30. What angle would the ramp need to be for the box to start sliding? Okay, so it's easiest to draw this out. So let's say, our box isn't initially on the incline, just straight up flat, right? Or let's say this is like a book. So it's a book on a table. I'm just gonna change it real quick just to help you guys conceptualize it. So we have a book on a table. Let me clean this up. So a book on a table. We have our box. Okay. So if we count, if we right off the bat, we want to find out sort of how much force we need to apply to this box to get it to start moving, right? So how do we do that? Well, force due to gravity or we do that whole equation where F equals mu static times with the N. Yeah. So then this force is going to be the force that we need to press on this object to get to start moving, right? So let's calculate that. So when we calculate it, we got 30 times mass, which is 30 kilograms times 9.8. All right, so what fraction of this, the force of gravity are we going to need? And what did we get? We got 88.2 newtons. Okay, so essentially we need a force in this direction, or either direction, in the horizontal direction, of 88.2 newtons to get it to start moving. Okay, so now we want to know what angle, right, between, let's say there's going to be an angle here. Let's say there's like a hinge right here. Just changing the scenario left and right. Hinge on this book, and we're going to open like the cover of this book, and our box is going to slide, right? So at what angle is it going to start sliding? Well, we're going to have it at an angle to where the force of gravity has an x in the x direction is going to have a force that is equal to 88.2 newtons. Okay, so how do we find that? Well, let's sort of draw our scenario out again. We have our book cover. Okay, our box. Okay, so this is the force due to gravity. This is the force in the x, right? So we know we need a force in the x direction of 88.2 newtons. We know what the force due to gravity is, right? It's just 30 times 9.8. So 30 times 9.8 is 294 newtons. Okay. So 294 newtons. Cool. So how do we find this angle right here? How do we find that angle? Well, I know if I break up my force due to gravity into its x and y vectors, right, I can go like this. And then this one down here, this x vector is going to be the same as that. So I can just pull that 88.2. So this is going to be the same. I know that this angle right here is going to be the same as that angle, right? So we could just use sort of our trigonometry, because we know the hypotenuse, we know the opposite. So if we use our sine, we can find this, right? So sine of our angle is going to be 88.2 divided by 294, okay? And then when we solve it all out, our angle that we need is 17.46 degrees. So we need to angle this book at 17.46 degrees in order to get this block to start sliding, because at that angle, our force in the x direction, if we define sort of this as our axes right here, our force in our x direction is going to be 88.2 newtons. Yeah, and again, if you guys have any questions on any of these problems, go ahead and comment in below. All right, so now we're getting into drag, okay? So the ball is thrown straight up in the air. What is the drag force on the ball when it is at its peak? What is the drag force just before the ball hits the ground if the ball is thrown 20 meters in the air, and the density of the air was 1 kilogram per meters power 3, and the effective area of the ball is 1 meter squared, and the drag coefficient is whatever that is, right? Okay, so two questions here, right? So the first question is, what is the drag force when the ball is at its peak? Okay, so maybe it would be smart to draw a diagram of what is going on, right? So we got our diagram over here. So we got a ball being thrown up, all right? It reaches, right, so part A, it reaches its peak. Okay, reaches its peak. What is the velocity of the ball at its peak? Anybody? 0. Yes, exactly. So the velocity of the ball equals 0 when it's at its peak. It's not moving, right? So if we go to our equation that we know for drag force, so D equals 1/2 C P A V squared. So, you know, if we plug in velocity here, velocity is 0, so our drag force is going to be 0. Drag equals 0. So how fast the ball is moving is going to affect the drag force, right? So the faster the ball is moving in air or object is moving in air, the more drag force you're going to experience, right? So in part B, what is the drag force just before the ball hits the ground if the ball is thrown 20 meters in the air, right? So we have to do a couple things here. We have to find the velocity, right? We have to find the velocity when the ball, just before the ball hits the ground. And then we could plug that into our equation and find our answer. So how do we do this? Well, let's see. What are we given here? We're given our displacement. Our displacement is 20 meters. We know the initial velocity, right? Let's say the initial velocity is 0 because we're measuring it from the peak to the ground, right? So we know at the peak, 0. What else do we know? We know the acceleration due to gravity, right? And that's really all we need to know, because if we use this equation of v squared equals v naught squared plus 2 times acceleration times displacement. We don't need time or anything like that, so we'll be chilling. Okay, so when we plug in our variables, so v squared equals 0 plus 2 times negative 9.8. And then our displacement here, if we define our axes right, our displacement will be negative, right? Because we're going towards the Earth. So let's say our displacement is negative 20 meters. So then when we calculate this all out, we'll get a final velocity of, what did I get? 19.79 meters per second. Okay, so we got our velocity now. Pretty simple, just plug all of our variables in. So drag force equals 1/2 the coefficient, which is 0.19 times, what was the other? The density, which is 1, right? Area, which is 1. And then velocity, 19.79 squared. Okay, so then the density is 37 point, or not density, drag force, 37.206 newtons. Cool. So that is our drag force when the ball hits the bottom.
All right, so number 5. Okay, so terminal velocity. What is the terminal velocity of a skydiver? What weighs that when density is that? Effective area of the main is that, and the drag coefficient is 0.19, right? So terminal velocity. Let's think of what is terminal velocity. Essentially, terminal velocity is the fastest an object can go because of drag, right? So usually, right, gravity is negative 9.8 meters per second, right? So it increases, your velocity increases by 9.8 meters per second for every second, right? Or your velocity increases by 9.8 meters per second every second, right? But since we have a drag force, there's a limit to how there's a limit to how fast we can go, right? So that'll keep increasing until we get to our terminal velocity. Another thing is like Elon Musk is trying to do these the speed rail thing, right? So one problem they're finding is like terminal velocity, right? The train can only go so fast because of air resistance. So what's their plan? Well, their plan is to make like a vacuum, right? Like some people think, oh, they're going to make a vacuum where it takes out all of the air and makes it you know, the thing's gonna be like levitating or something like that, and on like electromagnet. I don't know. I can't explain it. But anyways, their big thing is drag, right? They want to limit the terminal velocity, and to do that, they have to take away the air resistance. But we have air resistance, right? So let's look at our situation. We got our skydiver. So I'm just gonna do a dot diagram here. We got our skydiver, and what forces are acting on our skydiver? Well, we have the force due to gravity, right? And we also have our drag force. And at the terminal velocity, our drag force is going to be equal to our force due to gravity. Okay. So essentially, what does this mean? If at F net equals 0, our skydiver is not accelerating anymore, right? So F net equals 0 because our drag force and our force due to gravity are equal, right? So F net equals our drag force plus a negative force due to gravity, right? So if F net equals 0, then when we sort of solve, we have, well, essentially it's going to be the drag force equals the force due to gravity. Right, so then we know our force due to gravity is just m times g, right? So, so our drag force is just equal to m times g when we're at our terminal velocity. So if we plug this into our equation for drag force, right? So this equation that we've used before, drag equals 1/2 c p a v squared. And then we just substitute the drag force for mg equals 1/2 c, all that. That's essentially our terminal velocity equation. All right, all we have to do is solve for velocity. All right, so when we solve for velocity, this is what we get. We get 2 times mg over c dpa. Okay, so that's our terminal velocity equation. So pretty simple from here on. You just plug in the numbers and you'll get your answer, right? So terminal velocity equals 2 times our mass, 90.72, times gravity, 9.8, coefficient 1 times 1. Oh no, so our effective area is 2. And yeah, that's that, right? Yeah. So then when we solve, I didn't solve this in my notes. Hold on, the mass of 2 times 90.72 times 9.8 divided by 0.19 times 2. That square root of that equals, so our terminal velocity equals 68.405, let's say that, meters per second. Cool, so our terminal velocity for a skydiver is that fast, right? 68 meters per second. Yeah, if you guys have any questions, comment in the video. Please sign in if you haven't already. Help me out. Attend my office hours. The link's in the description, and then the times are posted on iLearn. Right, so good luck on all your tests and everything else.